me now introduce today's speaker. It's a real honor to have Professor Tony Liss with us today. Tony's been here since 1988 and is a professor of physics here at the university. His area of research is elementary particle physics, and in fact that's my area of research as well. And when I came here a few years ago, the one person who really helped get me started at the University of Illinois was Tony, and I really appreciate that. He's a tremendous asset to our department. He's won a number of awards, and I'm not going to go through the list. He's a fellow of the American Physical Society. He won the Sloan Fellowship. He also won the Xerox Faculty Award. Most recently, he's been the physics convener for the CDF experiment. This is a group of about 600 physicists who are doing an experiment up at Fermilab outside of Batavia. Tony will tell you more about that. And he was the person who oversaw all of the physics analyses. It's a very important position, and he did an outstanding job, and we're very proud of him. But the true measure of success, of a physicist is whether or not you've written an article for Scientific American. And that's what that is. The discovery of the top quark. Tony was instrumental in the discovery of the top quark about 10 years ago at Fermilab. He was the leader of the top quark working group at the time of the top quark discovery. And so you'll see there in some fine print. I told you should sit in the front row. Tony M. Liss was the author of that Scientific American article. Like I said, you've really reached it when you've written an article for Scientific American. So before we bring him on, I want to embarrass him yet one more time and point out that tomorrow is Tony's birthday. And since we have a nice, strong, energetic crowd this morning, can we sing one verse of Happy Birthday to Tony? All right? A 1, a 2, a 3. Happy birthday to you. Happy birthday to you. Happy birthday, dear Tony. Happy birthday to you. He's 29 years old today. Please welcome Professor Tony Liss.
Thank you. That was the best introduction I ever had. So if you did a little subtraction, you would have found out that I came here at the age of 13. Okay, so this is loud. I'm going to talk to you today about the intersection of particle physics and cosmology. There's been just a huge explosion in new results and new information from cosmology in the last 10 years or so. And there's just a tremendous number of exciting things that we're learning and new things that we had no idea. The universe turns out to be a particularly peculiar place, and we're learning all about that. And some of the ways we can understand how some of these peculiarities came about is at particle accelerators where I work. So as Kevin said, my field of expertise is high energy physics, but like many physicists, one of my prime areas of interest is actually cosmology. So I'm going to give you two views of the universe today. I'll give you the view from the high energy physicist perspective, and then I'll do my best to give you the view of cosmologists, people that study the universe. So let me start with the high energy view. And there's a large number of things that I could talk about, and so I'm going to give you a kind of survey today of some particularly interesting things, but I'm not by any means going to tell you everything. If you watch carefully, you will see there are various things that I've swiped off of websites, and all of the web addresses for those things, except this one, are there. And I would encourage you just to go, if you're interested in this stuff, just go poke around on the web, because there's a tremendous number of really good websites about cosmology and high energy physics in which you can learn a tremendous amount. So the high energy view of the world works something like this. We study the fundamental particles and the fundamental interactions between those particles, the forces between the particles, and until very recently we thought we knew pretty much everything, and everything was encapsulated in this picture, which shows you what the world around us is made of. And so the world around us is made up of quarks. There are 6 different types of quarks, and leptons. The most familiar of the particles that we call lepton is the electron that circulates around the nucleus in atoms. But there are heavier leptons as well. There are muons and taus, and then there are leptons that don't have any electric charge that we call neutrinos, which were actually invented and discovered around 1930 to explain some peculiarities in radioactive decay. But we now observe and study those particles. And the quarks also come in three families, just like the leptons do. There's the lightest family of the up and down quark, and then there's charm and strange, and then there's the top and the bottom quark. Now it turns out that the world around us is made just of the lightest family of these things. So, oh, that's not the right button. So a proton, for instance, in the nucleus of an atom is made up of two up quarks and a down quark. The neutron, which is the other component of the nucleus, is made up of two downs and an up. And then you stick an electron around them and you make a hydrogen atom. So everything around us in this room, you, me, all your friends, we're all made up of just the lightest family here. So one of the mysteries of particle physics, which I'm not really going to talk about today, is why there's anything other than just this lightest family. Now, the particles are held together by forces, and the familiar one that you'll know about is the electromagnetic force. That's the one that makes your socks stick to your pants when you take them out of the dryer. And then there's the force that holds the nucleus together, the strong force, and then there's a force that has to do with certain kinds of radioactive decay called the weak force. And of course there's the one holding you in your chairs, which is gravity. And I have to tell you right off the bat that we don't have a good understanding of gravity that allows us to put it in the same framework as the rest of these. So the forces are transmitted by force carriers. We give them a funny name called gauge bosons. The most familiar of those is the photon, which is the carrier of the electromagnetic force, and then there's a gluon, and there are some W and Z bosons. So here's a helium atom made up of two neutrons and two protons with two electrons circulating about it. The other side of this picture are these antiparticles, and they come about in the marriage of quantum mechanics and special relativity. In the early part of the 20th century, quantum mechanics was invented. Special relativity, of course, was invented by Einstein in the early 1900s. And when those two theories got together, physicists discovered that antiparticles had to exist. But they hadn't been discovered yet. As soon as the suggestion was made that they had to exist, experimentalists started looking for them, and sure enough, they did exist. The first antiparticle that was found is the anti-electron that was found in the cosmic rays. And now we study antiparticles on a regular basis. It's not Star Trek science fiction kind of stuff. Antiparticles, antimatter, actually does exist. And in fact, the accelerator at Fermilab, where both Kevin and I work, circulates counter-rotating beams of protons made up of two ups and a down, and antiprotons made up of two anti-ups and an anti-down. So antimatter is a very real thing, and it was something that was predicted theoretically before it was observed experimentally. Now, on the side of this picture, which deals with the forces that hold these particles together, we have four known forces, and I'm not counting gravity because we don't have a good theory of it, but so these four forces, the goal has always been to try and explain them in a unified way. This was something that Einstein tried to do for the latter half of his career and didn't succeed in, but we have now partial success in unifying these forces. We have, of course, unified the electric and magnetic forces into the electromagnetic theory, and that's something that is pretty easy to understand. You observe different electric forces and magnetic forces. You know, magnets and static electricity seem to be very different things, but in fact the magnetic field that you measure from magnets just has to do with electric charges that are circulating around, producing those magnetic fields. So there's really a single understanding of electric and magnetic forces, and we call that the electromagnetic theory. That's been known for quite some time. Over the last 40 years, the weak interaction, the weak force, has been unified with the electromagnetic force into what we imaginatively call the electroweak force. And this unification happens as you go from low energies up to higher energies. And we're just sort of at the verge of being able to study what goes on here at accelerators. We have almost enough energy. And if you've heard about the Higgs boson, which I'm really not going to talk much about today, but the Higgs boson comes from this electroweak force as you go to lower energies, changing into two different forces, the electromagnetic and the weak force. And that happens as a result of something that's called a phase transition. It's like when ice melts, it's a phase transition from a solid water state into a liquid water state. And this is a kind of phase transition like that as well. Then there's the strong force, which we have not successfully unified with these things, although there have been attempts to explain how that might happen. And if it happens at much, much higher energy. So our theory is working about up to here. There are ideas that I'll come back to of how it would work all the way up to very high energies, where all the forces would become manifestations of one kind of force. So how do we study these things? We study them at accelerators to a large extent. At accelerators, we accelerate particles up to extremely high energies, we smack them together, and we study what comes out of those collisions. And the reason that works is because of Einstein's famous equation E equals mc squared, which I'm sure you've all heard of. In this context, it means if you can get enough energy at a particle accelerator, you can make some new particles that have very large masses that you don't see in normal everyday life. Now, most of the time, those new particles that you might produce have very short lifetimes. So you make them, and then they immediately decay into something else. This is a picture of a kind of cartoon of a proton and an antiproton colliding and producing a pair of top quarks. And what actually collides in this collision are the quarks inside the protons. That's what these three things are in each one. You produce a top quark, and the top quark immediately decays into some other particles. And so it's this other stuff that you actually observe in a detector that you might build. So this picture shows you the Fermilab accelerator, which if you have never visited Fermilab, I encourage you to go. It's an open site, and there are self-guided tours, and they even have their own Saturday morning physics program, and it's a great place to visit. Okay, so that's the high energy view, and now let me give you the cosmological view. So the cosmological view works something like this. The universe began about 14 billion years ago in the Big Bang. The very early universe was extremely dense and hot, and it was so hot that all of these particles that I showed you in our picture of high energy physics, that whole array of particles, none of them were bound up into nuclei or atoms or anything, because the universe was too hot for them to hold together. So the heat of the early universe prevented these things from binding together. So what you have is just a soup of free quarks and leptons and whatever else there might have been, but no protons and neutrons or atoms or anything like that. And of course, there's lots of radiation, photons, in this soup as well. Now the universe expands, and as it expands, it cools, so the temperature of the universe goes down with time. And after about almost 400,000 years of this expansion, the universe is finally cool enough for electrons to bind to protons and make hydrogen atoms. So it takes 400,000 years before you can make an atom in the universe. It sounds like an extremely long time, but then we've had 13.5 billion years since then to go beyond that. Okay? So that's the picture of the universe. So how do we know that that's the picture of the universe? Well, like many things, we have a theory. The theory in this case is general relativity. I told you that we didn't have a theory on the same footing as the other theories in high energy physics that explains gravity. But that doesn't mean we don't have a theory of gravity at all. It means we don't have a theory of gravity at the particle level with force carriers and that kind of thing. But we do have what we refer to as a kind of classical theory of gravity, which is called general relativity, which is extremely successful on cosmological scales. So how do we know it's right? Well, it's been tested in great detail. And I'm not going to tell you too much about these tests, but it makes predictions, and people go out and test those predictions, and they turn out to be true. The first of those predictions that was tested was that light would be bent by massive objects. And so that was discovered almost immediately after Einstein made that prediction during a total eclipse of the sun, looking at a very distant star whose light was passing close to the sun. The bending of that light was directly observed. Then there are some peculiarities in the orbit of Mercury around the sun, which couldn't be explained by Newton's gravity, that got successfully explained by Einstein's gravity. And of course, the most famous prediction of Einstein's general relativity is the prediction of black holes. And so there has been much interest in black holes and many kind of indirect pieces of evidence that indicate that black holes exist. But I want to show you this movie, which I think is just remarkable, that I learned about only in the past few months. So this movie shows the orbit of stars over about a 10 or 12 year period close to the center of the Milky Way galaxy, our galaxy. The center of the galaxy is right there. Now you're seeing a blow up. Here's the date. Watch the orbit of these stars. This one, whose orbit is traced out for you, comes within 17 light days of the center of the galaxy. So that sounds like a long distance because you know light goes very fast, so the distance that light travels in a day is quite large. But that's on astrophysical scales extremely close. And so the shape of this orbit, the speed of this star, tell you that at the center of our galaxy resides a black hole. And you're able to rule out all sorts of other hypotheses. The most direct, solid evidence that a black hole exists that I know of, and I think it's the most solid that exists. And it's remarkable that there's a black hole at the center of our galaxy, and you could hear a whole nother talk on that, but not from me. But it turns out that black holes exist at the centers of almost all galaxies. But my point for today is really just Einstein's theory of general relativity has been tested in great detail, and all of the tests validate the theory. So we have great faith in the theory of general relativity. So why is it relevant here? It's relevant here because general relativity predicts that the universe is either expanding or contracting. The theory, as Einstein wrote it down first, doesn't admit anything other than expanding universe or contracting universe. Einstein, by the way, was not too happy with this because in his time he thought the universe was static, just sitting there. I'll come back to that. But it was shortly observed by Hubble in 1929 that the universe is in fact expanding, that galaxies are moving away from us, and the speed with which they're moving away from us is proportional to how far away they are. So it looks something like this. Think of a loaf of bread that is rising in the oven, and you're sitting at some point in the loaf of bread, and there are raisins scattered within this loaf, and the bread is rising. The speed with which they're moving away from you depends on how far away they are. If this is 1 second between there and there, then this raisin, here you are right there, this raisin is moving from 5 to 10 centimeters. It's moving 5 centimeters per second. But this one that started 10 centimeters, it's moving at 10 centimeters per second. They're from you, at the rate from you they are. And that's the sign. So I'll wrote down a law. It looks very simple. The speed or whatever you're looking at moving away is proportional to the distance. And this constant is called the Hubble, somewhere around miles per hour for every million light years. How would one measure such an expansion? Well, there are two ingredients. There's the distance things are away, and there's the speed they are away from you. The distance you measure by something called a standard candle. And a standard candle is just an object that has a known intrinsic brightness. That is, you know how bright it is at its source. And you measure the apparent brightness here on Earth, and that, compared with the intrinsic brightness, tells you how far away it is, because you know how things get dimmer as they go farther away. Hubble used something called Cepheid variable stars, whose period was proportional to their brightness. So he could measure the period independent of how far away they were, and from that he could calculate how bright they actually were. Then the speed is measured by something called the Doppler effect. And this is a little cartoon that shows you the Doppler effect. If you have a source emitting waves, like light waves, and it's moving towards you, so you're over here observing the light waves coming towards you, you see a frequency which is shifted higher. In terms of light waves, that means it's shifted into the blue because the source is moving towards you as it's emitting waves. If you're on the other side and the source is going away from you, then you see a frequency that's shifted down into the red in terms of light waves. And so by looking at the redshift of particular frequencies of light that are characteristic of emission from these objects, you can measure a redshift and tell how far away, how fast these things are moving away from you. It's just like when you hear a police car or a fire engine on the street going past you. As it's coming towards you, you hear the siren, and then when it goes past you, you hear a Doppler shift between the higher frequency as it's coming towards you and the lower frequency as it's going away from you.
Could you make that sound again, please?
Only if you double my sound. Okay, so we believe the universe is expanding. There's evidence for it, and in fact, in the early 60s, two physicists at Bell Labs, Penzias and Wilson, discovered what we call the cosmic microwave background. They discovered it by mistake. They were looking for something from somewhere in the Milky Way galaxy. They built this big antenna to measure radio waves, and they went out with it. Look, there was annoying noise that they just couldn't get rid of no matter what they did. And it turned out that annoying noise was the cosmic microwave background. And the cosmic microwave background are the photons that come from the Big Bang and suddenly become free when atoms form 400,000 years later. So it works something like this. In the early universe, you've got all these free electrons, and you've got photons, these little squiggly things, bouncing around, and it's one big gas of stuff. And everything is sort of at the same temperature. So the photons are bouncing of the charges are bouncing off the photon, and it's what we call equilibrium. And then the universe is expanding, and it's 380 form, and some photons are free. And now you see these in the sky, because now you have an electrically neutral universe, but neutral atoms, and so we don't interact with them anymore. Go on their merry way free, and so what you see is in the photons is the temperature of the universe at 300,000, but then it gets frequencies because the universe is expanding. So I should tell you about one, which is that I will use interchangeably the concept of temperature and energy. So those things are intimately related, and when I said that these things are all at the same temperature, the temperature of the photon corresponds to the energies of the photons, and the energies corresponds to their color, their frequency. Okay, so the cosmic microwave background that Penzias and Wilson saw was these photons that were up at 380,000 years after the Big Bang. So it agreed beautifully with the predictions and the theory of the Big Bang and the expanding universe, which shifted the frequencies of these photons down into the microwave region. So everything's working beautifully. We know that the universe began in the Big Bang. We understand how atoms were formed in the early universe, and this cosmic microwave background comes from the point it was freed up at the point where atoms were found. But there are some major questions here. So one question is why the cosmic microwave background is so uniform. And so that works something like this. These three pictures show the temperature, or the spectrum, if you like, of the microwave background on the sky. So on the sphere of the sky that's surrounding us, mapped out into this oval. And there are three different scales of temperature here. So in the upper scale, blue would be absolute 0 degrees Kelvin, and red would be also really, really cold, 4 degrees Kelvin. And there's no variation whatsoever. So the cosmic microwave background on this scale is absolutely uniform. Now you blow the scale up so that blue and red are separated by only 0.008 of a degree. And now you start to see this pattern. There's red up here and there's blue down there. That pattern comes from the motion of the solar system through the rest frame of the microwave background. So the solar system is moving in this direction. And so when you look in that direction, the photons that you see are redshifted because you're moving towards them. And behind you, they're blue shifted because you're moving away from them. So that's just the motion of the galaxy. Now you remove that motion of the solar system. You remove the motion of the solar system, and you go to a much finer scale, where the differences between red and blue are only 0.008 of a thousandth of a degree Kelvin. And you see a pattern like this. And that pattern contains an enormous amount of information that I'll tell you about. But let's ask the question why this is so uniform, and why is that even a problem that it's uniform? Well, if you think about what happened 380,000 years ago, and you look at the sky, even regions of the sky that are relatively close to each other are more than 380,000 light years apart. That means they couldn't have communicated with each other. And in fact, the further back in time you go towards the Big Bang, the worse that problem becomes. The smaller the region over which things could have communicated with one another. So why is that a problem? Well, if they can't communicate with each other, if they can't exchange information, if photons from one region can't get to the other region and scatter off the particles there's no reason at all why they should be at the same temperature. They could be at completely different temperatures, but we see this amazing uniformity. And that's called the horizon problem. And I'll come back to the horizon problem and its solution in just a minute. But first I want to look a little bit more at this map, because this map contains an enormous amount of information about the early universe. It is a snapshot of fluctuations in the temperature of the photons, or the frequencies of the photons, at 400,000 years after the Big Bang. So where do the fluctuations come from? Well, it turns out that on relatively small scales in this picture, those fluctuations come from sound waves that were propagating in the very early universe. Just after the Big Bang and propagating for 400,000 years until these photons were freed up. And so by looking at the sizes of the fluctuations in the temperature here, you can learn about the geometry of the universe, because you can measure the frequencies of these sound waves, which have to do with the size of these fluctuations, and from that you can calculate a wavelength. And that wavelength tells you what kinds of correlations you should see over what angular scales on this picture. And that gives you a side of a triangle. And the other triangle is you sitting on Earth observing this. You can learn about the geometry of the universe. That is, whether the universe is closed or open or flat. So let me talk about that shape of the universe a little bit. If you assume that the universe is just matter and radiation, nothing else, and I'll talk about that assumption later, then there's a critical density, a density in grams per cubic centimeter of the universe, above which the universe will, I think I have this backwards, above the critical density, the universe collapses, and below the critical density, the universe expands forever. So the universe is expanding, and gravity's pulling it back together, trying to slow down that expansion. If there's enough gravity, then the expansion of the universe will stop, and it'll collapse back on itself. And if there isn't enough gravity, then the universe goes off and expands forever. Right in between those 2 points is a critical density where we say the universe is flat. It turns out that that cosmic microwave background picture tells you that the universe is flat. It is neither open or closed, but flat. It's quite mysterious to learn that the universe is flat because this is a very unstable point. The density of the universe is something that changes with time because the universe is either expanding or contracting. So if it's expanding, the density is getting less with time, and if it's contracting, it's getting greater. And you don't expect to find the universe right at this special point of the critical density. Physicists don't like coincidences. It could just be that we got lucky and we happen to be here at a time when the density is 1, but that's not a very appealing answer. So we like to look for something else, a reason why the universe is actually flat. So there's a solution that comes from particle physics. And the solution was invented in around 1980, and it's called inflation. And inflation is something that works like this. In the very early universe, when these forces that I talked about earlier were somehow unified all into one force, there's a phase transition that happens here as they break, as the universe cools, which is going to the right in this picture, and the electroweak force breaks off from the strong force. That phase transition releases energy into the universe, and that energy drives an expansion of the universe, which is extremely fast. It's exponential. So you start off with a Hubble kind of expansion. Then there's this very short but very dramatic expansion, exponential expansion, and then you go back to the Hubble expansion that we see today. What that means is that we're sitting here observing the universe. If you assume that it's just the Hubble expansion, then you come back along this line, and the radius of the observable universe, you take your observable universe today and you contract it back to some very early time, and it's about 1 meter in diameter, which is still too big for photons to have communicated across that meter. So you don't expect temperature, you don't expect the temperature to be the same in different parts of the sky. But if you allow for this inflation picture, then today's visible universe comes all the way down here to some incredibly tiny initial point where you solve this problem of having everything at the same temperature, because it's so small that in fact you could have communicated parts of it, and so photons could interact with it all over the universe and cause it all to be at the same temperature. So that solves, this picture solves this horizon problem. And it also implies that the universe would be flat today. So it solves the flatness problem as well. So it's possible that when we have a working theory of how these forces are unified here, and we're moving in that direction, that we will understand in detail the dynamics of what went on here. Okay, so I want to talk about telescopes and accelerators. The cosmological results I've told you all come from telescopes like the Hubble telescope, and then the high energy part comes from accelerators like the Tevatron. So what do they have to do with one another? What they have to do with one another is this. Here's the history of the universe from the Big Bang all the way to us sitting out here observing it today. The universe, so this first thing here is time after the Big Bang. So here we are at 13, 14 billion years. This is the temperature of the universe, and this is the energy that that temperature corresponds to. So in the very early universe, we have this Hubble expansion, then we have this inflation, And now we have all these free particles. All of our elementary particles are free. Nuclei begin to form here as the unispools. Then out here at 380,000 years, we have atoms forming, and that's where the cosmic microwave gets freed up, and we see it today. Up here, you see the names of a bunch of accelerators. So at the Fermilab Tevatron, we are probing energies that correspond to the universe at like 10 to the minus 13 seconds after the Big Bang, just very shortly after the Big Bang. The LHC at CERN, which will begin running in a few years, goes a little bit farther back. This is a log scale, so you don't gain very quickly, but it has 7 times the energy of the Fermilab Tevatron. So you get to go a little bit back towards the early universe. So we really are directly probing at accelerators the conditions that happened at the early universe in an attempt to understand what physics goes on there. There are some dramatic successes to this picture. One of them is the ability to predict the abundances of light elements in the early universe, from hydrogen to lithium. These elements were made in the early universe when the nuclei formed from the quarks. And we can calculate what the abundances are, and the calculation looks like this curve, and it depends on a parameter which is the density of baryons, that is, particles like protons and neutrons that are made up of quarks. It depends on the density of those particles in the early universe. And so from this calculation, you learn that the density of those particles has to be about 3% of this critical density. That is the density that's needed to close the universe. And it predicts correctly the abundances of lithium and different species of helium and deuterium. And in fact, about 1 out of 10 nuclei in the universe is predicted to be a helium nucleus, and that's in fact what we observe. So this is a very successful picture. However, it raises a big question. I told you that we believe that the universe is flat. That is, the energy density of the universe is this critical energy density, which is about 10 to the minus 29 grams per cubic centimeter. So if that's density is the critical density, but the density of baryons, that is protons and neutrons, is only 3% of the critical density, it raises the question, what's the rest of the stuff in the universe? So most of the stuff in the universe is not normal matter. It's not the stuff that you and I are made of. It's something else. And it gets worse. Because now we can measure the density of matter by making various astronomical measurements. So we say that there's something called dark matter, which is whatever the matter is that we don't, that isn't the normal stuff that we're made of. It's an idea that goes all the way back to 1930, when one can measure the speed of stars that are rotating around. And from the speed of the stars, you can measure how much gravitational pull there has to be inside the orbit of the star around the center of the galaxy. Because if there isn't enough gravity, the star is just going to go flying off. The fact that it's captured in an orbit in this galaxy means that there has to be a certain pull in to keep it from flying away. When you compare that pull with the amount of matter that you see in the stars, it doesn't add up. It's not even close. So there is matter that's not visible as stars in the galaxies. There's dark matter. And you can do this on bigger scales with black clusters. These are now clusters of galaxies, which also orbit around each other. And you can play the same game with the speed of the galaxy out here and the total mass that you measure inside its orbit, and that doesn't add up either. And when you play this game, you find that the density of matter that you need for these things is about 3/10 of the critical density. The density that you observe is much less than that. It's only a few percent. So you learn that the total density of matter is 3/10 of the critical density. the density of baryons, protons, and neutrons that you see is only a few percent. So right away you've got 27% of something that is not normal matter. But then you still have this problem with the fact that the universe is flat. And so there's 70% of the universe that doesn't seem to be matter at all. And I'll come back to that. But let's address first the question of what the dark matter is. So we know it's not normal stuff. We know it's not protons and neutrons. What could it be? And of course, high-energy physicists have a bunch of ideas what it could be. One of those ideas used to be neutrinos with mass. It was recently discovered by high-energy and nuclear physicists that neutrinos have mass. But it turns out that neutrinos with mass don't work very well for the dark matter. So we go to idea 2, which is that there's a new set of particles called supersymmetric particles, which could make up the dark matter. So remember I told you that special relativity and quantum mechanics got together and predicted a whole set of antiparticles. So for every particle there was an antiparticle. Well, the same thing happens when you try to marry Einstein's general relativity with quantum mechanics. It seems to need a partner for every single particle we have, particles, antiparticles, what have you. So all of those particles I showed you on the first picture, they all may have a supersymmetric partner that we haven't discovered yet. And then, of course, there are lots of other ideas that this one turns out not to be right. But let me tell you just briefly a little bit about supersymmetry, or SUSY as it's called. Every quark and lepton and every force carrier has a supersymmetric partner in this theory. These supersymmetric particles would be made in the early universe, lots and lots of them, because the early universe had lots of energy. Most of them decay away quickly, just like that top quark in the picture decayed rapidly, except for the lightest one, which isn't allowed to decay in the theory, because you have to conserve the number of these supersymmetric particles. So if you've got one that's very light, there's nothing lighter for it to decay into, it can't go anywhere, because it's not allowed to decay into normal particles only. That lightest supersymmetric particle could be the dark matter. It could be what makes up almost 30% of the energy density of the universe. And we can look for these things at accelerators, and we do. Haven't found any yet, but there are reasons to expect that we're sort of on the threshold of being able to produce supersymmetric particles at accelerators, because we need a lot of energy in order to make them. And they have a very well-defined signature. So if we succeed in making them, we will know, and we may be able to answer the question over the next few years of what the dark matter actually is. There are some good reasons to believe in this theory that have to do with Einstein's dream of a unified field theory. So this picture shows you for our three forces, electromagnetic, strong, and weak, the strength of the force as you go up in energy. So we can measure this with accelerators. We can measure how strong forces are. And then you do the kind of grade school level thing of just plotting the strength versus energy straight lines and seeing if they all go to one point, because you want these things all to be one force at very high energies. This is where we are now. They don't go to one point. But if you add a supersymmetric theory, you can change the slopes of those curves so at some very high energy they actually do. There's some motivation to believe that supersymmetry may solve the problem. If it's not supersymmetry, not to worry, we can make whatever it is at an accelerator provided we have enough energy. How much time do I have? 2 hours?
Yeah, that's right. Cut it off by 1 more.
So I told you that we've now talked about 30% of what the universe is made of. Only a few percent of it are neutrons and protons, like you and me. 25 or so percent is this dark matter that we're trying to figure out. But the universe appears to be flat. So there is 70% of the universe that's missing, because the critical density is apparently 1. So what is that? Well, it has been dubbed dark energy because it's not matter and we don't see it. And dark energy was actually discovered, or apparently discovered, by looking at very distant supernovae. So one uses supernovae as a standard candle. Certain types of supernovas, one can, by looking at their spectra, one can measure their intrinsic brightness, and then you can measure their apparent brightness, and that tells you how far they are away, or the dimness. And then you can measure their redshift. So just like Hubble did with these Cepheid variables, you can play the same game with supernovas. When you do that, you can go out to very large distances far away in the universe, and you discover that the universe is accelerating. The expansion of the universe is accelerating. It's not slowing down like you would expect it to do, because you think the gravitational pull is going to slow the expansion. It's actually speeding up, apparently because of this other 70% of the universe that's dark energy. So what would Einstein do about this problem? Well, he already solved this problem. Remember I told you that he didn't like the fact that general relativity predicted an expanding or contracting universe? So he added another term to his equations called the cosmological constant, which prevented gravity from pulling the universe back together. It was a repulsive force that he introduced into the equations. Once Hubble discovered that the universe was expanding, he pulled it back out and he said, oh, that was just a stupid mistake. But even Einstein's stupid mistakes were brilliant insights. So the cosmological constant has now come back in the guise of this dark energy. It's just what's needed. It's a repulsive force that can make the universe, the expansion of the universe, accelerate. Now the cosmological constant comes naturally out of particle physics. In particle physics, the thing that we call the vacuum isn't actually completely empty. It has some energy density because quantum mechanics allows us to make little particle-antiparticle pairs that wink in and out of existence. So in particle physics, the vacuum isn't a vacuum the way we normally think about it. It's empty space with some energy density, which is exactly what's needed for the cosmological constant. So it sounds like particle physicists are on the ball and we've solved this problem. But unfortunately, we're off by 120 orders of magnitude. So the cosmological constant that you would like to predict from particle physics is just, it's the worst prediction I know of in all of science. It's so bad, this is not new, it's so bad that people just thought, well, there must be some mechanism we haven't thought of that's going to make this thing zero. There's some other piece that we're going to add on that's going to cancel out, and it's zero. So nobody worried too much about this. But now it appears not to be zero, it just appears to be 120 orders of magnitude smaller. And that's a much harder thing to figure out than, there's something we haven't thought of that makes it go away entirely. Supersymmetry helps. If you add supersymmetry into your theory, then you're only off by 55 orders of magnitude. So it's a mystery at the moment. Finally, I want to talk about one last thing, and I'll go quickly because I'm sure you want to get to your tours, and that's the question of where all the antimatter went. Our picture of high energy physics leads you to conclude that equal amounts of matter and antimatter are produced in the early universe because they're symmetric. They have the same masses, the same properties, everything. But when we look out at the universe, we don't see any antimatter. If there was antimatter out there, we would see its annihilation with matter into photons, and that is not observed. So the universe appears to be all matter. So we need a mechanism to create some kind of little imbalance between the matter and the antimatter in the early universe. And you don't need very much. You need about a part in 10 to the 10. Because there's so much matter in the early universe, a very small excess of matter over antimatter leaves you with quite a bit of matter when you're done canceling the two out. So you go from just a tiny excess of matter to what we have in our universe plus lots of photons from the annihilation of all the other stuff. So where does this come from? Well, again, particle physics to the rescue, because we have a mechanism for a difference between the behavior of matter and antimatter, and it's called CP violation, and it was the 1980 Nobel Prize in Physics for the discovery of CP violation, and it leads to a very slightly different behavior between the rates of decays of particles and antiparticles. So you would make equal amounts in the Big Bang. Then in the decay, you end up with slightly more matter than antimatter, and then you have the annihilation that leaves only matter. That's just what's needed. And again, particle physics to the rescue. We're on our way to understanding this problem. It's been measured. These decays have been, this phenomenon of different matter and antimatter behavior has been measured. There's a whole accelerator at SLAC devoted to making this measurement. And so we know a tremendous amount about this. And unfortunately, what we observe with our fundamental particles is not enough to explain the early universe. So although we see the phenomenon we need, it's not strong enough to explain even this part in 10 to the 10 difference. So there has to be another source, and that other source might come from the neutrinos, which we just discovered have a mass. Not at all what we thought. For the 70 years of our knowing about neutrinos, it was always thought that they were massless. The fact that they have mass means that they may show this phenomenon of CP violation. And it might be that we're here because of neutrinos. There are experiments that are getting ready to look for this phenomenon. The experiments are quite amazing because neutrinos almost don't interact with anything. They're very hard to see. And this phenomenon is very subtle. And in order to see it, you have to have a very long beam of neutrinos. So here's an accelerator at Brookhaven in Long Island producing neutrinos with a detector to observe them in South Dakota. So here's the universe as we know it. It's completely different from what we thought it was as recently as 10 years ago. The universe is made up mostly of stuff that isn't us. We only make up around 4% of the universe. There is another 23% of the universe which is some kind of matter, but we don't know what it is. It could be supersymmetric particles. It's something that we can study in accelerators if we have enough energy to make this kind of matter. And that's what we're doing now and will continue for 10 years. And then there is this mysterious stuff about which we've just learned in the last few years, which actually makes up most of the energy density of the universe, this dark energy. So we were all very proud of our standard model of particle physics very recently. We're still proud of it. It's a great theory. It works, but it has its limitations in this little slice of the pie. And so it turns out that most of what the universe is, we don't know, and we don't yet know whether we have a theory of it. So the theories will continue to evolve. The theories are very successful in their range of where they can be applied. There's lots of new things being discovered on a weekly basis, and the theories get adapted, make new predictions. We test with experiments and accelerators and observations of cosmology. Over the next years, I think there's going to be tremendous excitement as we begin to pick away at these problems and learn about what these new things are, and these things we have no real understanding of yet. And I think that we're almost guaranteed to have significant new insights and new surprises over the next 10 years, over the years in which those of you who are interested in going into science will begin your careers at an extremely exciting time. No matter how much we do and how much we understand, there will always be a few rare phenomena that no matter how hard we try, nobody can ever explain.